Hello and welcome to the Flip Learning video on 3D Pythagoras. In this video I'm going to take you through how we extend our application of Pythagoras' theorem to 3 dimensions. So by the end of this video you will be able to use Pythagoras' theorem to calculate different lengths within 3-dimensional figures. So we can use Pythagoras' theorem to solve problems in 3 dimensions which involve calculating the length of a right-angled triangle that will arise somewhere within our 3-dimensional shape. Because Pythagoras' theorem is initially used in 2 dimensions, if we bump this up to 3 dimensions, we will need to use Pythagoras' theorem more than once. So for a little bit of terminology, looking at the cuboid there, the diagonal denoted by AC is what we would refer to as a face diagonal because it is a diagonal length that goes along the face of our 3-dimensional shape. The diagonal denoted by AF is what we would call a space diagonal because it is a diagonal that goes through the space of our 3-dimensional shape. So that's what I'll be referring to from here on out. There are 2 different methods that we can use to calculate the length of a space diagonal, which are what the majority of 3-dimensional Pythagoras questions are. We can either use Pythagoras' theorem twice, first of all to calculate the length of the face diagonal, then using this in the height to calculate the length of the space diagonal, or we can sort of draw from the magnitude of a vector in unit 3, and we can consider the space diagonal as a vector and then calculate the magnitude. So you will see more of that later in the course, so don't worry too much if you don't understand that yet. So first of all, for example 1 there, we are given the cuboid with dimensions 5, 7 and 8 centimeters, and we are asked to calculate the length of the space diagonal denoted by CE. So what I'm going to do here is I'm going to show you how to apply both of those methods. So method 1, just a reminder, was where we calculate the length of the face diagonal, then the space diagonal. So our face diagonal in this case is AC, and in red I have highlighted the right-angled triangle that we will be using. So our right angle is at B, which means that the 5 centimeters and the 7 centimeters are the 2 shorter sides of our triangle. This means that the side that we are looking for, AC, is our hypotenuse, and if it's the hypotenuse, we are squaring the 2 shorter sides and adding them together. So that's going to be 7 squared plus 5 squared, 49 plus 25, which gives us 74. However, that is not the length of AC, that is the value of AC squared. So what we then need to do is take the square root of 74, which is 8.6 centimeters. Once we've got that, we can then move on to calculating the space diagonal. So as you've hopefully seen there, I have shifted what I have highlighted. What we are now looking at is the triangle highlighted in red and then filled in green there. So it has a height of 8 centimeters and then a base of 8.6 centimeters, that face diagonal that we just calculated. Our right angle is at A and we are looking for the hypotenuse CE because again we're looking for the hypotenuse, squaring both sides and adding them together. So that's going to be 8.6 squared plus 8 squared, 73.96 plus 64. Which is going to give us 137.96, but again that is not the value of the space diagonal, that is the space diagonal squared, so we square root that and we get 11.75 centimeters. The second method for this one is where we consider the space diagonal as a vector. So what that means is it is the vector with components 5, 7, 8. Whenever we calculate the magnitude of a vector, we square all of our components, add them together, and then square root it. Magnitude of a vector is just Pythagoras' theorem in 3 dimensions. So you can use this if you are confident with it in order to solve 3D Pythagoras questions. So that's going to be the square root of 64 plus 49 plus 25, which is equal to the square root of 138. When you do that, you get 11.75 centimeters, the exact same as the question before. Both methods will get you full marks. Now, 3D Pythagoras will often arise in context questions. The example that we've got here is from the 2018 paper 2, and it is question 16. So it came up in the calculator paper, and it was quite late in the paper as well. So we've got Chris who wants to store his umbrella in a locker. That locker is a cuboid with dimensions 40, 40 and 70 centimetres. We are told that the umbrella is 85 centimetres long, and he plans to put it from corner P to corner M, essentially meaning that the umbrella would be the space diagonal. He thinks it will fit in the locker. Is he correct? So quite a bit going on there. We need to calculate the length of the space diagonal, PM, and we then need to compare that to the length of 85. If PM, our space diagonal, is greater than 85, then yes, it will fit in the locker. If it is less than 85, then Chris's umbrella will not fit in the locker. Again, I'm going to take you through both methods for this one. So first of all, if we are looking at method 1, that was where we calculate the face diagonal, then the space diagonal. So again, in red, I have highlighted the right angle triangle there that we are looking at. It has two shorter sides of 40 centimetres each. Again, we're looking for the hypotenuse, so a squared plus b squared, 40 squared plus 40 squared, which is going to give us two lots of 1,600, which is 3,200. Square rooting that, you get 56.57 centimetres. After that, we are going to use that 57.57, the face diagonal, and the unused height of 70 centimetres to calculate the length of PM, again highlighted in the red triangle in the diagram below. So we're still looking for the hypotenuse, 70 squared plus 56.57 squared. That gives us 4,900 plus 3,200.16. That gives us 8,100.16. Square rooting that, and we are getting 90 centimetres. So we've done all the work. We now need to relate that back to the context of the question. The context of the question again was saying that Chris has an 85 centimetre umbrella. Will it fit in the locker? Well, what we can say there is that the space diagonal is 90 centimetres and Chris's umbrella is 85 centimetres. So it will fit in the locker as the umbrella, 85 centimetres, is less than the space diagonal, the maximum space of the locker, 90 centimetres. So just like before, I'm also going to do this using the magnitude of a vector. So the space diagonal PM has components 40, 40 and 70. So what we're doing there is the square root of 70 squared plus 40 squared plus 40 squared. So that's 4,900 plus 1,600 plus another 1,600, which gives us the square root of 8,100, which should be looking pretty familiar, because when we do that we get the same answer of 90 centimetres there, and we can draw the same conclusion from that. So that brings us to the end of the flipped learning video on 3D Pythagoras. Hopefully by now you can apply Pythagoras' theorem to calculate lengths within a 3D figure. The main takeaway from this video is that there are two methods, two different approaches that you can use to do it. Both are totally valid, both will get you full marks. Just pick whichever one makes the most sense to you. Thank you very much.